Welcome students. So today we are going to start our new chapter, that is the some p block elements, chapter number 11. Okay. So first thing which we are going to discuss here is about the p block elements. So what are the p block elements? The first question arises here. So if we are going to see our periodic table, so in our periodic table there the elements which are present at the right hand side of our periodic table, okay, on the extreme right hand side of the periodic table, here you can see the elements which are present. They are termed as the p block elements. Now why they are termed as p block element? The first question arises here, why they are termed as the p block elements. So the reason for the p block element them to be called as the p block element is that, first let's see the definition of the p block elements. The elements whose the elements whose valence electron are filled in the p suborbital are called p block elements. P block elements. Okay. So if I am taking an example for boron here, so the electronic configuration for boron is 1s2, 2s2, 2p1. Similarly, for aluminium, it will be 1s2, 2s2, 2p6, 3s2, 3p1. For nitrogen, it will be 1s2, 2s2, 2p6, 3s2, sorry, nitrogen, I am writing wrong here, sorry. It will be 1s2, 2s2, 2p3. Okay. For phosphorus, it will be 1s2, 2s2, 2s2, 2p6, 3s2, 3p1, sorry, 3p3. Okay, 3p3. Okay. So like this here, you can see the examples which I am taken here. Okay. For fluorine also, I can take the example as 1s2, 2s2, 2p5. For chlorine, it will be 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Oxygen also, carbon also, okay, carbon family, all this will be having the same electronic, means the same property, that the valence electron will be filled up in the p orbital, p suborbital. So hence these elements, means the elements from the group number 13 to the elements till group number 18, they all are termed as p block elements. Okay, because the valence electron has been filled out there in the p block there, or p subshell. Okay. So here, which are the elements, which are the groups which comes here? So the group number 13, that is called as boron family. Okay. The group number 13, that is the boron family, that are called as icosahedrons. Okay, icosahedrons. Next, group number 14, that are called as tetragens. Okay, tetragens. Then group number 15, that are pnictogens. Okay, pnictogens. The group number 16, that are chalcogens. Okay, chalcogens or chalcogens, whatever you want to call. Then group number 17, halogens. Okay, and the group number 18, inert gases. So in the class 11th, we are going to study these two particular groups. We are going to study the chemistry of the group number 13, that are the icosahedrons and tetragens. And the 15 to 18 group elements will be studied out in the class 12th. So these two group, that is group number 13 and group number 14, will be present here in the will be studied out here in the class 11th. So let's see what are isocagens. Okay, icosagens. Okay, icosagens. What are icosagens? So this icosagens is been made from two words, that is icosahedron and gen. So icosahedron, it is related to the geometry of these elements. Okay. So icosahedron means a polygon, a regular polygon which have 20 faces. Okay, a regular polygon which will having how much? 20 faces. So they will be termed as what? They will be termed as the icosahedrons. Okay, icosahedrons. And as the elements of the group 13 are producing such kind of geometry, so they are termed as what? They are termed as the icosagens. Okay, icosagens. Next, tetragens. So tetragens means the elements of the group number 14, which are carbon or silicon or germanium. Okay, all these elements have the property that they possess 4 electrons in their outermost shell. For example, carbon, it is 1s2, 2s2. So here you can see that in the outermost shell it is possessing how much? 4 electrons. And due to this reason, they possess tetravalency. They possess tetravalency, and hence due to production of tetravalency, they are termed as tetragens. Okay, so this is the for rule by which we are going to, this is the two groups, that is group number 14 and group number 13, which we are going to study here in our class 11th. So let's have some general introduction to these two groups, that is group number 13 and group number 14. So group number 13, icosagens, their name. The general outer electronic configuration here, it will be ns2 np1. I have discussed this you before only. Okay, that the boron, it will be having 2s2 2p1, while the aluminum will be having 3s2 3p1, while the gallium will be having 4s2 4p1. Okay, next the uh, after gallium, indium will be having 5s2 5p1. Okay, like this the different electronic configuration, the general electronic configuration here, it will become ns2 np1 for the icosagens. Next, highest oxidation state which can be achieved out here by this group elements are +3. Okay, the highest oxidation state which can be achieved here, it is +3. Highest observed oxidation state, okay, means the other oxidation state which are generally observed here, it will be +1 also. Means with +3 they can also make +1 ion, means +1 oxidation state can also be represented by them. Next, group number 14 elements, tetragens. So tetragens general electronic configuration is ns2 and np2. Okay, such as for carbon it is 2s2 2p2, for silicon it is 3s2 3p2, for germanium it is 4s2 4p2. So here the general electronic configuration, it will become ns2 np2. Okay, outermost electron will be having 4 electrons. Outermost shell will be having 4 electrons. Now the highest oxidation state, that is the group oxidation state, here it will be +4. The other observed oxidation state here, it can be -4 also, because as all the elements, generally all the elements which are present there in the group 14, it will be termed as non-metals only. So hence, when we are considering their covalencies, so when they are bonded with the covalent bond with the elements which are present there on the left hand side of the periodic table, so they will be behaving as a more electronegative element as comparison to that of the elements which are present on the left hand side of the periodic table, and hence there they will show -4 oxidation state. Okay. Next is the +2 oxidation state can also be represented by them. Okay. So these are some general properties or general uh, relations related to the group number 13 and group number 14 elements. Now, let's move to the next topic, that is the group number 13 elements. Let's start the thorough study of the group number 13 element, that is also called as icosahgens or boron family, as the boron is the number one element here, the first element in this group. So it is also termed as the boron family also, or icosahgens. Now, for the icosahgens or the boron family, how many elements are there? So total 1, 2, 3, 4, 5. Total 5 elements are there. There are 6 elements, but the last element, that is the sixth element, which is generally termed as the radioactive element, it is not been considered as the part of the icosahgens, because the reason is that only a few atoms have been discovered out there. Okay, so hence the study for that particular element is not completed. So hence it is not been included while we are studying the group number 13 there. So first is the boron element in the group number 13. Then comes the aluminium. Then comes the gallium. Then comes the indium, and then comes the thallium. Okay. Generally, these elements are also termed as post-transition metals also. Okay. They are also termed as post-transition metals. Now, at general condition, means at 293 Kelvin temperature, the boron is also solid, aluminium is also solid, gallium is also solid, indium and thallium is also solid. The atomic number for boron it is 5 plus 8. For aluminium it will become 13 plus 18. For gallium it will become 31 plus 18. For indium it will become 49 and plus 32. For thallium it will become 81. So here you can use this magic numbers, that is, if you are knowing the atomic number for boron, so using this magic number, that is plus 8 plus 18 plus 18 plus 32, you can calculate the atomic number for other elements also of this particular group, that is the group number 13 icosahgens. Okay. Now, what are the isotopes of the elements which are present here in the group number 13, that is what are the isotopes for icosahgens? So the isotope for boron it is B11. Okay, the atomic mass of this element will be 11. Next, aluminium's isotope is aluminium 27. Okay, aluminium 27. Next is the, for gallium it is gallium 69. For indium it is indium 115, and for thallium it is thallium 205. Okay, so they are having one isotopes and which are presented here. Next, atomic masses. So for boron it is 10.81. Okay, it is 10.81 and 11 also, which is an isotope of boron. So hence 10.81 is the atomic mass. Next, aluminium 26.98. Next, for gallium 69.72. For indium 114.81. For thallium 204.38. Next, electronic configuration. So for boron it will be helium 2s2 2p1. For aluminium it will be neon 3s2 3p1. For gallium it will be argon 3d10 4s2 4p1. For indium it will be krypton 4d10 4s2 5s2 5p1. For thallium it will be xenon 4f14 5d10 6s2 6p1. The atomic radius here 1.92 is the atomic radius for the boron. For aluminium it is 1.84. For gallium it is 1.87. For indium it is 1.93, and for thallium it is 1.96. Okay. Next, density. Density for boron it is 2.34, aluminium 2.70, gallium 5.91, indium 7.31, and thallium 11.80. Melting point and boiling points for boron 2350 Kelvin, 4273 Kelvin, as it is solid, so it is having very high melting point. But aluminium is having the lower melting point, that is 9933, and lower boiling point than that of the boron, that is 2792, that is 2792 Kelvin. Gallium, it is having more lower melting point as that of the aluminium and boron, and it is one of the most easily meltable, okay, easily meltable elements or metal present on the earth. So it can be melted out at only 302.76 Kelvin temperature. Okay, means a little bit more than that of the room temperature. Okay, next is the boiling point, which is 200 to 2502 Kelvin temperature. Next, 429 for indium. So here also you can see that it is also having very low boiling point, melting point temperature, and for thallium also it is 577 only. The boiling point it is 2300 and 1746. So here you can see that on moving down here, the gradually, not gradually, but very drastically, the change in melting point and boiling point is been observed out here. So now let's discuss why this kind of properties are being seen out here. So today we are going to first discuss about the atomic radii and the ionic radii. Atomic radii and the ionic radii of the group 13 elements. What is the trend and what is the relationship between them for the atomic radii and the ionic radii? So here, so for atomic radii and ionic radii, if I am talking, so we know that we have studied this particular trend in the periodic classification of element, that on moving down in the group, means if you are talking about boron, aluminium, then gallium, then indium, then thallium. Okay, so here on moving down, the atomic radii or the ionic radii must increase due to increase in the number of shell. This was the general rule. But here, when we are talking about the atomic radii for the aluminium, which is 143 picometers, for gallium it becomes 135. Okay, for indium it is 167, and for thallium it is 170. While for boron it is 85. So as boron is the first element in the group, so it must have the smallest atomic radii, it is correct. Then for aluminium it increases with the increase in the shell number. But for gallium, here you can see there is a decrease here or decrement in the atomic size. So the reason here is that the electronic configuration for gallium, we have studied here that the electronic configuration for gallium it is 3d10 4s2 4p1. Okay, argon 3d10 4s2 4p1. So due to the presence of this d orbital here, okay, due to the presence of this d orbital, which is not present here in the aluminium case, what will happen? The size, due to the presence of this d orbital here, the inner pair effect will occur, or the shrinkage of the atom will occur, and due to this reason the size of the gallium will decrease out here. Okay, the size of the aluminium will decrease out here, and here we will observe that the atomic radii or the ionic radii for the gallium also, if I am talking about the ionic radii also, so in the case of ionic radii the gallium will be showing the gradual increase. The ionic radii for aluminium it is 53.5, but for aluminium 3 plus I am talking, है ना, not for aluminium 1 plus, it is for aluminium 3 plus, means when 3 electrons has been removed, then it is only 53 picometer, while for gallium it will become 62 picometers for Ga3 plus. Okay, so Ga3 plus. So here you can see that there is a gradual increase, while here it is showing that it is having a gradual decrement here. The reason is that due to the presence of this 3d10 uh, orbital here, the size of the atom of gallium reduces. Okay, next is the ionization enthalpy. Okay, next is the ionization potential or ionization enthalpy. Ionization enthalpy. Okay, so here for ionization enthalpy for boron, aluminium, gallium, indium, and thallium. So here, in the case of boron, when we are going to see the ionization enthalpy, so ionization enthalpy for first element, okay, means IE1, it will be 801 kilojoule per mole. For aluminium, it is 577 kilojoule per mole. For gallium, it is 578. For indium, it is 588. For thallium, it is 590. So the trend for the ionization enthalpy in the periodic classification of element, we have studied that the ionization enthalpy or ionization potential increases when we are moving down in the group. As the atom size increases, so with the increase in the atom size, the tendency to release the electron from their outermost shell increases out there. Okay, so due to this reason, what will happen? The ionization enthalpy will decrease out there. But here you can observe that in the case of gallium and aluminium, when we are moving down here, we will see that there is an increment in the ionization enthalpy here. It is very negligible, but this particular change here, it is due to the presence of 3d orbital here. As 3d orbital is present in the gallium, so what will happen here? Here, shielding effect will be produced. Okay, shielding effect will be produced. And what is the shielding effect? So here, if I am talking about the gallium, so here first shell, second shell, and at the third shell, as d orbital is there. Okay, in the third shell, the d orbital is there. Okay, so that d orbital will be having more energy as comparison to that of the 4s or 4p shell here. Okay, so due to this reason, what will happen? They will just shield out the 4s and 4p orbital also, and they will not allow this particular orbital's electrons to be removed out there easily. Okay, and hence due to this reason, what will happen? The energy which will be required out here to remove the electron from the p shell or the s shell here, it will become larger as comparison to that of the previous element which was present there. So hence here we will see that there will be a slight increase in the ionization enthalpy when we are moving down from gallium from aluminium to gallium here. Okay, and here after that you will see that there is a gradual increase there in the indium and thallium. But here when you are moving from aluminium to gallium, there you will see that there is a gradual increase here for the due to the presence of the shielding effect here in the metal in the atom of the gallium. Next, the melting point and the boiling point. The melting point and boiling point. Okay, so here we have observed that the melting point of boron, it is very, very high. Okay, here you can see that the melting point of boron, it is 2315, while the other metals which are present here in the group number 13, they are having very low melting point as comparison to that of the boron. So what is the reason? The reason is that the icosahedron structure of boron. Okay, the icosahedron structure of boron, it is responsible for the high melting and boiling point of boron. So boron is also present in solid form, but it is harder solid as comparison to that of the other elements which are present there in the group number 13. Okay, it is having a harder crystalline structure, and hence its melting point is also very high. It is generally a black colored solid, and it is having a non-metallic nature while it is present with other metals, but it is having a non-metallic nature here in the group number 13. Okay, it is generally a non-metal here. Okay, and generally it is considered as sometime also non-metalloid also. Okay, now here the aluminium or the indium, even gallium. Gallium is the softest metal of this group. It is one of the softest metal of this group with a very, very low melting point. While aluminium and other are having a considerable melting point, while the gallium is having a very, very low melting point, it can be melted out very easily at home also. That much lower melting point is there for the gallium. Okay. Next is the electropositive character. So electropositive character for the group number 13 element is that electropositivity. Electropositivity. So here we will see that the boron, it is a non-metal here. The boron is a non-metal here and it does not possess high electropositive nature. Okay, while it possesses the electronegative nature as comparison to the other elements which are present there in the group here. That is aluminium, gallium, indium and thallium. Okay, what happens here in the case of boron here is that boron is a non-metal due to presence of its more allotropes as comparison to that of the other elements here. Okay, and due to this reason, other elements behave also. It is present as the head of the family, that is upside of the group, and we know that on moving up in the group, we will see that the non-metallic character is increasing out there. Okay, next is the oxidation state. Okay, the oxidation state for the group 13 elements. Oxidation state. So oxidation state, if we are talking about, then the oxidation state, generally the oxidation state for the group 13 element, it is plus 13 or it can be plus 1 there. Okay. Boron, it is having a plus 3 oxidation state, and also in very accepted condition, we can see that boron can behave as a plus 1 element also. Okay, it can show the oxidation state of plus 1 also. Next, here the oxidation state for the elements here, it will be showing the trend like this. Okay, and we will see that thallium will be having more stability in plus 1 state, while the aluminium will be having more stability in the plus 3 state. Okay, so we will see that the plus 1 state will be decreasing out here. The plus 1 oxidation state will be decreasing out here. The stability of the plus 1 oxidation state will be decreasing out when we are having less smaller element here in the group 13. And the thallium, it will be having the higher stability in the plus 1 state than indium, gallium or aluminium. Okay, so this was the trend for the elements which are present here in the group number 13. In the next class, we will continue with the chemical reactions or the chemical properties of the group number 13 elements. So for today, I am closing the class here only. In the next class, we will continue with some of the more properties. So thank you.